Okay. So, what form does it take? We want to derive a Rodrigues type formula for the Hermite polynomials, an analog of Rodrigues formula for Hermite polynomials. So, let us begin with the expression 7.4 displayed in the slide. Okay. So, what is Qnx? Qnx is the nth derivative of e to the power minus x squared. When you differentiate e to the power minus x squared n times, what are you going to get? We are going to get a polynomial times e to the power minus x squared. Try it for n equal to 1. So, differentiate e to the power minus x squared minus 2x into e to the power minus x squared. That e to the power minus x squared factor gets killed by e to the power x squared that you see in equation 7.4. The e to the power x squared and the e to the power minus x squared cancel out and you get simply minus 2x. So, when n equal to 1, we get q1x equal to minus 2x. What is q0 of x? You are not differentiating at all. If you are not differentiating at all, d0 of e to the power minus x squared is simply e to the power minus x squared, which cancels with e to the power x squared. So, q0 of x is 1. So, q0 of x is 1, q1 of x is minus 2x. Now, differentiate e to the power minus x squared twice and multiply by e to the power plus x squared. You are going to be left with a polynomial of degree 2. By induction, you can prove that Qnx is a polynomial of degree exactly n. Now, let us assume m is less than n, and we shall show that these Qn's are also orthogonal in the following sense: integral over r Qnx Qmx e to the power minus x squared dx is going to be 0 if m is not equal to n. So, m is not equal to n and m is less than n. So, how do we prove the orthogonality? How do you prove that this integral is 0? Let us do this. So, let us look at this qm factor. The qn factor has an e to the power x squared that has killed the e to the power minus x squared, and we are left with qnx e to the power minus x squared is simply going to be nth derivative of e to the power minus x squared. And the qm factor is left alone. You see the middle equation displayed in the slide. What is the next step? You simply integrate by parts. The d to the power n that you see should transfer and it should fall on qm. So, we have to integrate this by parts repeatedly n times, transferring all the derivatives to the factor qm. So, let us see, every time you differentiate, every time you transfer the derivative onto the first factor, what do you get? You get a boundary term. What is the boundary term? So, the first iterate, the boundary term is going to be qmx into n minus first derivative of e to the power minus x squared, evaluated at minus infinity and evaluated at plus infinity. Remember that the e to the power minus x squared is rapidly going to 0 at infinity and minus infinity. So, the boundary terms will drop out. So, the derivative simply shifts over to the qm factor. Of course, there is a minus 1 factor. So, when you transfer all the derivatives to the factor qm, you pick up a minus 1 to the power n factor and you get integral over r d to the power n qmx e to the power minus x squared dx. But remember that qm is a polynomial of degree how much? M, and m is strictly less than n. So, what you are doing in the last displayed equation, the integral on the right hand side, you are looking at d to the n qmx, that is the nth derivative of a polynomial of degree m with m strictly less than n, and that is 0. So, we have established that integral over r qnx qmx e to the power minus x squared dx is 0 if m is not equal to n. The orthogonality of these polynomials 7.4 has now been established. Now, we must appeal to the fundamental orthogonality lemma. Now, look at the vector space. Now, we got a vector space of polynomials. The set of all polynomials form a vector space over the reals. On this vector space, we can provide an inner product. What is the inner product? inner product of f and g equal integral over r fx gx e to the power minus x squared dx. We are working over real vector spaces. We are working over real vector spaces, no need to put the bar on the gx. So, in this real vector space, we have got two sets of orthogonal polynomials, namely q0, q1, q2, etc. and f0, f1, f2, etc. In the last slide, we have proved the orthogonality of q0, q1, q2, and the previous slide, we have proved the orthogonality of f0, f1, f2, etc. So, now we have got two sets of orthogonal polynomials. Degree of q0 is 0, degree of f0 is 0. q0 is 1 and f0 is 1. q1 is minus 2x and f1 is a linear polynomial. q2 is quadratic and f2 is quadratic. So, what does it mean? It means a linear span of q0, q1, q2, qn is the same as a linear span of f0, f1, f2, etc. fn for every n running from 0 to infinity. So, by the fundamental orthogonality lemma, we infer that fnx must be a multiple of qnx, namely fnx must be equal to cn times qnx for every n equal to 0, 1, 2, 3, etc. Just for your reference, let us recall the statement of the fundamental orthogonality lemma. Suppose V is a vector space endowed with an inner product with respect to which v0, v1, v2, etc. and w0, w1, w2, etc. are two sets of orthogonal non-zero vectors, and assume that span of v0, v1, v2, vk is the same as span of w0, w1, w2, etc. wk for every k, k equal to 0, 1, 2, 3, etc. Then there exists scalars ck such that vk equal to ck wk for k equal to 0, 1, 2, 3, etc. We have discussed this fundamental orthogonality lemma in the previous module when we discussed the Legendre polynomials. I am just recalling that for you. So, we have the fact that the fnx, the Hermite polynomial fnx is cn times qnx, which basically means that the Hermite polynomial fnx is cn times e to the power x squared nth derivative of e to the power minus x squared. So, we have almost arrived at the explicit formula for fnx. There is only one small thing missing: how to find the constants cn. How did we do it for Legendre polynomials? There we put x equal to 1 because Pn of 1 is 1. And so, that is how we fixed the constant Cn to be 1 upon 2 to the power n into n factorial. Here, there is no universally accepted convention for normalizing the Hermite polynomials. We shall make our own convention. We shall seek the Cn, the constant Cn, such that the resulting vectors are unit vectors with respect to the L2 norm. That is how we will do. We will select the Cn in such a way that the Hermite functions are orthogonal and of unit length. So, let us turn to that. So, normalizing the Hermite polynomials. So, again, let us look at Qnx. Qnx is e to the power x squared nth derivative of e to the power minus x squared. So, let us carry out the differentiation e to the power x squared into n minus first derivative of minus 2x into e to the power minus x squared. So, let us apply the Leibniz rule for the n minus first derivative of a product. The first term will be minus 2x into n minus first derivative of e to the power minus x squared, and there is an e to the power x squared. So, you get qn minus 1 minus 2 times n minus 1 into e to the power x squared into n minus 2 derivatives on e to the power minus x squared. I applied the Leibniz rule for the kth derivative of a product of two functions. The binomial coefficients come in. Now, look at the second term. The second term has now been written as LOT. So, it is minus 2x times qn minus 1x into LOT. What does LOT stands for? LOT is abbreviation of lower order terms. Now, repeat it. Qn minus 1x will be minus 2x into qn minus 2 plus LOT, lower order terms. So all in all, you'll get minus 2x the whole squared qn minus 2 plus LOT, etc. Ultimately, you will get minus 2x raised to the power n plus LOT, where LOT is lower order terms. So we see that the nth derivative of qnx, the nth derivative of qnx is simply going to be minus 2 raised to the power n into n factorial. That's all we get when you differentiate qnx n times. We will need this fact when we do the normalization. Okay, so let us compute now. Integral minus infinity to infinity qnx e to the power minus x squared, the norm of qn with itself. What is that equal to? Integral minus infinity to infinity qnx, one qnx has kept as it is, in the other qnx I put the definition. The e to the power x squared and the e to the power minus x squared cancelled out, I am left with dn e to the power minus x squared. Integrate by parts n times, transfer all the n derivatives onto the qn factor, boundary terms cancel out as before. Every time you integrate by parts, you will pick up a minus 1, you get minus 1 to the power n, integral minus infinity to infinity, nth derivative of qnx into e to the power minus x squared dx. But the nth derivative of qnx we have just seen is minus 2 to the power n into n factorial, minus 1 to the power n, minus 1 to the power n, cancel out. We get 2 to the power n into n factorial, integral minus infinity to infinity, e to the power minus x squared dx, our old friend the Gaussian, whose value is root pi. So we get the normalized Hermite polynomials Hnx is e to the power x squared d to the n e to the power minus x squared divided by the square root of this number that we have got, the square root of 2 to the power n factorial root pi. So it is pi to the power 1/4 in the denominator, 2 to the power n by 2 into root n factorial in the denominator, display 7.6 in the slide. Okay, so that's how you normalize the Hermite polynomials. So the normalized Hermite functions are e to the power minus x squared capital Hnx, n from 0, 1, 2, 3. It forms a complete orthonormal basis for L2 of R. What we have shown is that they are orthonormal. But now we have to show completeness. What does completeness means? You take linear span of these, take its closure. You are supposed to get the whole of L2 of R. It's a basis for the Hilbert space. Basis in the sense that you take the linear span and you take its completion. You get an orthonormal basis for L2 of R. We have proved everything except completeness. Right now we shall not prove completeness. Maybe we will get back to this later sometime, but let us continue the discussion. These functions are extremely important. These normalized Hermite functions, which form a basis for L2 of R, an orthonormal basis for L2 of R, are extremely important in quantum mechanics and the study of the Schrödinger equation. We have already indicated in module 4 that these functions are eigenvectors of the Fourier transform operator on L2. Recall that the Fourier transform is an operator from L2 to L2. And what does it do? When I apply the Fourier transform, if I call script f as a Fourier transform, take f and take its Fourier transform, take its Fourier transform again. What do you get? You get 2 pi times the reflected f, namely f hat hat of x equals 2 pi times f of minus x. There is a sign flip. You should go back and look at the Fourier inversion theorem and understand where this sign flip comes from and where does the 2 pi come from. So what is the period of the Fourier transform? F hat 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 hat. Take the function f and apply the Fourier transform 4 times. You will get 2 pi squared times f. So when I iterate the Fourier transform 4 times, I get 2 pi squared times the identity. So what are the possible eigenvalues of the Fourier transform? If lambda is an eigenvalue of the Fourier transform, then lambda to the power 4 will be an eigenvalue for the Fourier transform applied 4 times. Remember, in linear algebra, if you have a matrix A and if lambda is an eigenvalue of A, lambda squared is an eigenvalue of A squared, lambda cube is an eigenvalue of A cube, lambda to the power 4 is an eigenvalue of A to the power 4. Here we have an operator, the Fourier transform operator, and you are composing it 4 times. And so if lambda is an eigenvalue, then when you compose it 4 times, you get lambda to the power 4. But when I compose the Fourier transform 4 times, what do you get? You simply get 2 pi squared times the identity map. The identity map has eigenvalue 1, and 2 pi squared times the identity map has eigenvalue 2 pi squared. So what do we conclude? We conclude that if lambda is an eigenvalue of the Fourier transform, then lambda to the power 4 equals 2 pi squared. So what are the eigenvalues of the Fourier transform operator? The eigenvalues of the Fourier transform operator are root 2 pi minus root 2 pi, I root 2 pi and minus I root 2 pi. The Fourier transform has only 4 eigenvalues, plus minus root 2 pi plus minus I root 2 pi. Now we shall show that these Hermite functions are the eigenvectors of the Fourier transform. And these eigenvectors form a complete orthonormal basis. So these are all the eigenvectors, there are no other eigenvectors. So the Fourier transform, all the eigenvalues have been identified and complete orthonormal basis of eigenvectors have been identified. So the job is done. So now let us recall how to prove that the Hermite functions are the eigenvectors of the Fourier transform operator. We have done this before and this is a recap. Let us quickly recapitulate this. The differential equation is what? Y double prime minus 2xy prime plus 2 lambda y equal to 0. When lambda equal to n, the solution is hnx. Now we are looking at e to the power minus x squared by 2 hnx. So what is the change of variables? Y e to the power minus x squared by 2 equals u. So what differential equation does u satisfy? U satisfies the equation u double prime minus x squared u plus 2 lambda y plus 2 lambda plus 1 u equal to 0. So 2 lambda plus 1 u equal to 0. When you take the Fourier transform of this last equation, we have seen that the last equation is invariant under the Fourier transform. So in other words, if u is a solution of the same equation, u hat is also a solution. Now the differential equation for u has no u prime term. There is no u prime term. So the Wronskian of two solutions is constant by the Abel-Liouville formula. The Abel-Liouville formula from elementary ODE says that the Wronskian is going to be constant, and if u is a solution, u hat is also a solution, the Hermite function is a solution, so its Fourier transform is also a solution. But the Hermite function e to the power minus x squared by 2 capital Hnx is in the Schwarz space, it is rapidly decreasing. So its Fourier transform is also in the Schwarz space. Can they be linearly independent? Suppose if these two are linearly independent, if Hn and Hn hat are linearly independent, then what will happen to the Wronskian? The Wronskian will be non-zero constant because they are linearly independent solution of a ODE without the u prime term. But on the other hand, how do I calculate the value of this constant? Allow the x to go to infinity. When x goes to infinity, you have got two elements in the Schwarz class. I take the Wronskian and allow the x to go to infinity, I am going to get 0. So the constant must be 0. How can that happen? We have two linearly independent solutions, right? That's a contradiction. So Hn hat must be lambda n times Hn. When I take this Hermite function and take its Fourier transform, I am supposed to get a multiple of it. In other words, Hn is a eigenvector for the Fourier transform with eigenvalue lambda. So each of the Hermite functions is an eigenvector for the Fourier transform as an operator, and we have got a complete list of eigenvectors for the Fourier transform operator. One final example before we continue with the theory. We have looked at L2 of the real line. Let us look at L2 of the open interval 0 infinity. This is another classical example with applications to quantum mechanics. Here again, we shall construct an orthonormal basis of functions, and these functions are called Laguerre functions. And what are the Laguerre functions? The Laguerre functions are of the form ln x e to the power minus x, where ln x is a certain polynomial. These polynomials are called Laguerre polynomials. As in the case of Hermite functions, we shall begin with the Laguerre differential equation. Where does the Laguerre differential equation comes from? It also comes from the Schrodinger's equation. You should look at the book by Arthur Beiser, Perspectives of Modern Physics, for the relevant background from physics to understand how this comes from. Again, the Laguerre functions will be complete orthonormal in L2 of 0 infinity. We shall again not prove the completeness right now. We shall only establish the orthogonality. So, let us begin. Laguerre differential equation xy double prime plus 1 minus xy prime plus lambda y equal to 0. Unlike the Hermite's equation, this differential equation has a regular singular point at the origin. So, you cannot expect a power series solution method to work. In fact, it is not going to work. You are not going to get two power series solutions converging in a neighborhood of the origin. Anyway, what you must do is you must appeal to the Frobenius's method. When you appeal to the Frobenius's method, it turns out that when lambda is a non-negative integer, you do get a polynomial solution. That is a fact, and I leave it to you to verify that. Using the Frobenius's method, you will get one power series solution, and that power series solution will truncate when lambda is an integer, positive integer. And these polynomial solutions are as before denoted by f lambda of x. And these f lambdas will be mutually orthogonal. So, when lambda equal to n, there is only one polynomial solution. There cannot be two polynomial solutions. Again, the Abel-Liouville formula will tell you why. The Wronskian will have a singularity at the origin. So, it cannot possibly have two polynomial solutions, and this so the Laguerre differential equation when lambda is a non-negative integer has only one polynomial solution up to scalar multiples, and so that is unambiguous except for the scalar multiple. The scalar multiple will be fixed by the normalization. We shall select the scalar multiple in such a way that ln x e to the power minus x has unit L2 norm. So, how do you understand the orthogonality of the Laguerre polynomials? You do that by converting the Laguerre differential equation in self-adjoint form. So, multiply the differential equation by e to the power minus x, then the first two terms combine to become an exact derivative. It is x e to the power minus x y prime prime plus lambda e to the power minus x y equal to 0. From this, we immediately infer the orthogonality of the Laguerre functions. So, let us record it as a theorem. The functions ln x e to the power minus x by 2 is an orthogonal system of functions in L2 of 0 infinity, namely integral 0 to infinity ln x lmx e to the power minus x dx is 0 if m is not equal to n. Proof is again simple. Ln x satisfies which differential equation? X e to the power minus x ln prime prime plus n e to the power minus x ln equal to 0. Lm satisfies which differential equation? X e to the power minus x lm prime y prime plus m e to the power minus x lm equal to 0. What next? Well, multiply the first by lm, multiply the second by ln. Integrate from 0 to infinity, integrate by parts, subtract, and you will get the orthogonality. Now, we need to normalize. The normalization I will leave as an exercise for the audience. Here we will stop this lecture. Thank you.